Hello. So, we are going to do another, that's rough. We're going to do another virtual lecture today. We're picking up where we left off with Tuesday, or in your case, I guess that would be yesterday. We're picking up with yesterday's lecture. So we're going to be on page 12 of the notes, which I've got in front of me, and on slide 40. Right here. So if you're following along with the notes or with the slides on your own, that is where we're starting. So we talked a little bit in the previous virtual lecture about how energy travels through ecosystems and how organisms obviously eat other organisms, right? About how everything from producers all the way up to apex predators, as you can see in this graphic, the energy is traveling through the ecosystem. So in order to talk about how that energy travels through ecosystems, we need to understand energy a little bit better. And so that's what we're going to start with today. So this is a trophic pyramid, as it states. And all it is it's showing how energy flows through an ecosystem. So you can see it says it shows the decrease in usable chemical energy available at each succeeding trophic level in a food chain or web. So basically, you start at the top up here, right? And it's got 0.01% energy. Whereas at the bottom, the producers, remember those autotrophs, they make their own food, auto meaning self, they're self-feeders. These guys have 100% energy because they use that energy from the sun, created their own food, and so they have 100% energy. But each level as it goes up, that energy amount is reducing. So this is where we left off yesterday and where we're going to pick up today. Starting out with the first law of thermodynamics, also known as the law of conservation of energy. All of you probably already know this. If you don't, that's fine. But it's just the idea that energy is never created and it's never destroyed, but it can change the form that it's in. So, for example, an automobile, a car, is going to change its chemical energy to mechanical and heat energy because using the chemical energy, it's using that gasoline, and as it's driving down the road, the combustion is causing heat and it's causing movement. So mechanical and heat energy instead of chemical energy. But the main point of all this is that no matter which form that energy is going from and going to, that energy, there's the same amount constantly. So the total amount of energy is always going to stay the same, even if the form of the energy has changed. That's important to note. The second law of thermodynamics is just the idea that when energy is transformed, the quantity of energy remains the same. So that's what I just mentioned. It's the second law of thermodynamics. Generally, this is like how I live my life. All of the systems are moving towards randomness rather than order. So in the natural order of things, it's more likely for things to move towards chaos than organization. Same. In living ecosystems or in living systems, as energy gets transformed, some is lost to the environment in the form of unusable heat. So if we go back and we look at this guy right here, we start with 100, we end with 0.01% energy. So what we're losing, like it says, is energy in the form of unusable heat. So that's where that energy is going as it decreases as you move up the trophic pyramid. Hello. So ecological efficiency is just the percent of usable chemical energy transferred as biomass. It's important to note that it is being transferred as biomass from one trophic level to the next. So again, we know I love my words. If you break that down, bio obviously means life. Hopefully we know that, and we know what mass is. So when that energy gets transferred, it's from organisms eating other organisms, whether they be plants or animals, and it's moving from one trophic level to the next. And so this is where we came up with the 10% rule. We, as if I came up with it. I didn't. I'm going to teach it to you, though. The 10% rule is just the idea that as energy is transferring from one trophic level to the next, only about 10% of it gets passed on. And that makes sense, right? Because when you go back And oh, we got one right here. When you look at this right here, that pyramid, it's a pyramid, right? It gets smaller at each level. And it's even got the math breakdown for you over here. So if you've got 20,000 calories, kcals per year, whatever, you've got this. You've got 20,000 here. And that's going to be stored as biomass. We start with our light energy. These primary producers are autotrophs. They're self-feeders. As they make their own food, they've got 100%. They've got 20,000. So they're good. They're golden. There's a lot of them, and it's a big, wide bottom portion of the pyramid. Now, a little bit of that energy that they have goes off as heat, right? And so when the primary consumers, these little cute guys over here, when they eat those autotrophs, those primary producers, they are only getting 2,000. So they have to eat quite a lot of these plants in order to be able to survive. So they have to eat more. And then that cycle continues as you move your way up until you get up to the apex predator, the quaternary consumers. In this case, it looks like it's a hawk. And they're only getting 2 instead of 20,000. So it goes down by quite a bit. So each level, each animal is having to consume more than the one below it. And you can also see in each level, you're losing heat every time. Now, as these guys are eating, when you eat, obviously that the unusable portions of what you eat are going to get gotten rid of as waste. So as these guys are eating, they're using the bathroom, they're dying, they're leaving carcasses of what's left of the animals after they've eaten what they wanted. And that stuff is the waste and dead matter that's going to end up going to the decomposers. We talked about those a little bit the other day, right? They're nature's cleanup crew. They help break down dead things. So we like decomposers. So this right here basically sums up how entire ecosystems work, right? And how that energy is transferring throughout the ecosystem. Hopefully that was useful. So the law of 10%, important to remember. Ecosystems are obviously going to be different. Depending on the ecosystem, they are going to be a little bit different in regard to how productive they are. So the amount of energy that's available is going to determine how much life the ecosystem can support. So if we put that on like the most basic level possible, if we've got, if every coyote has to eat 10 rabbits a year, that's insane. But if every coyote has to eat 10 rabbits a year to live, and you've only got 20 rabbits, then you're definitely going to only be able to support 1 or 2 coyotes, right? So whatever energy is available is going to determine the amount of life the ecosystem can have. Hopefully that kind of helps that make sense. So what that brings us to is the conclusion that the more energy available at the base, at the bottom of that food chain, the more energy there'll be for consumers at the top of the pyramid. And that makes sense, right? Because we're really wide. We've got lots of options down here. So if, let's say, this primary producers category was cut in half, then each level above it would also be cut down, right? Until you might not even be able to get all the way to the top because there might not be enough energy available for the top predators to survive. So the less energy available at the base, the fewer animals the ecosystem is going to be able to support. Oh gosh, okay. So, oh, my lights went off. Hello? Please turn back on. Oh, we did it. Okay. So most solar energy, as we know, all of the energy on Earth, everything alive, it all comes from the sun. What's wild is that only 1% of solar energy that's hitting producers is being captured by photosynthesis. So 99% of it is reflected or it goes through producers or doesn't get absorbed by them. Only 1% of that solar energy is hitting producers, so those autotrophs, those plants, things like that, and going through photosynthesis to create food for those plants. And then 60% of it is lost to respiration, right? Getting released. And then 40% supports the growth and reproduction of the producers. So that's kind of explaining how that 10% rule came around. And when right here, when it mentions GPP and NPP, we're going to dive into those two. GPP refers to the gross primary productivity. So the total amount of solar energy that producers in an ecosystem capture through photosynthesis over a given amount of time, right? I don't know if you guys are familiar with like the GDP, or when you do your taxes, they'll ask for your gross income. So it's before taxes. So this is before anything comes out of it. We're just looking at the total amount of solar energy that is being captured. And it's also the rate at which the producers are converting that solar energy into chemical energy, right, through photosynthesis, in the form of biomass found in their tissues. So that might sound a bit complicated. We are going to break it down further. Meanwhile, your net primary productivity is the energy that's actually captured by producers in an ecosystem minus the energy producers respire. So respiration is going to lose some of that that energy. So, for example, if I'm doing my taxes and it says, what was your gross income for 2020? I'll give the total amount of money that I made. But if they want my net income, that's going to be the total amount of money that I made minus the taxes that I've already paid. So in this case, gross primary productivity is the total amount of solar energy that they captured, all of it. But the net primary productivity is the amount that they really got to use, because you're subtracting the amount that they lost through respiration. Okay? So like we said, net primary productivity is just gross primary productivity minus respiration. Glucose is obviously what gets produced during photosynthesis, glucose and oxygen. Some of that glucose is later used to supply energy to make those cellular processes happen, while the rest of it gets laid down as new material or biomass. So if I showed y'all my plants in my classroom tour, so when my plants are absorbing that sunlight, they're absorbing that sunlight, some of the glucose that is created from photosynthesis is just going to go towards keeping the plant going, keeping it alive. Meanwhile, what's left over can be used for growing the plant and creating new tissues, new biomass, making the plant bigger. Lost my spot. So if you look at the major world ecosystems, really broken down into biomes, you can see what their biomass is versus their net primary productivity. So net meaning that's the amount that they actually get to use. And number one it's probably an obvious answer, is going to be the tropical rainforest, right? We call them the lungs of the earth because they are putting out a ton of oxygen. Those plants in those areas are killing it. They're like really, really, really going through photosynthesis in a good way. They're producing tons of oxygen, and their net primary productivity is 20, meaning that they can keep growing. They can keep getting bigger because they have enough primary productivity, enough energy left over after they have completed their necessary systems with the glucose. They have some left over with that net primary productivity so that they can continue to grow bigger. Meanwhile, the one with the least net primary productivity is going to be the desert shrub, which makes sense. There's not as much biodiversity. There's not as much leafy green plants, right? So it's not, it makes sense. What's wild and what a lot of people don't realize is that the oceans actually produce even more oxygen, and they are much more alive with plants than even the tropical rainforest. Not by much, it's close, but the phytoplankton and other tiny floating things that go through photosynthesis on the surface or in the top layers of the open ocean produce a lot of our world's oxygen. Oh, I went too far. So that is actually it for today. Today's was a little bit shorter. We're stopping on page 17, which means that when we pick up with our next set of notes, we will start on page 18 and whatever the slide after this one is with the biogeochemical cycles. Remember that if you have any questions after you reviewed this, hold on to those. Take notes as you're going. If you have any questions, make sure you write them down, and we will have a Q&A again every day, and you can ask any questions you might have then. But hopefully this was helpful and easily understandable, and I'm going to sign off. Thanks for watching, guys.